Have you guys ever played with one of these Spirograph sets? Have you ever wondered what the math behind them is? Let's figure it out. You're probably pretty familiar with one-to-one functions at this point. Take f of x is equal to x squared, for instance. Each x value has a corresponding y value. We can represent this also with a set of vectors. We can then describe each of these vectors using its own associated equation. For x, we can say g of t is equal to t, and for y, we can say h of t is equal to t squared. Using these two functions, we can now describe our original function using a set of parametric equations. Let's break down how this works. Our parametric function, p of t, takes an input parameter t and applies it to a matrix composed of two equations that together describe the direction and the magnitude of the vector sum of a horizontal and a vertical vector for all points along some interval of t. That's a bit of a mouthful, so take a second to rewind if you need to. What we are doing here is applying a technique called parametrization. This is a fundamental and profoundly powerful concept in mathematics. Describing curves using parameters is much more versatile than typical one-to-one functions. Watch what happens if we switch the functions in our matrix, for instance. Our original function rotates 90 degrees clockwise to produce a curve where each x value can have multiple corresponding y values. Modeling is like building a puzzle. You identify all the pieces and figure out how they fit together. Our Spirograph is composed of circles, so let's start there. Parameterizing a circle is pretty simple. Let's say point P is the distance r from the origin. To get to P, we need to find two equations whose sum is always equal to the radius of the circle. Recalling basic trigonometry, we know the relationships for sine and cosine must have the same hypotenuse length for a given right triangle. These equations can hence be rearranged to describe our vectors. With the basic circle figured out, let's take a second to understand what we are trying to model. The Spirograph is a small gear of radius r1, with holes spiraling out from its center at a distance d, that rolls along the inside of a circular track of radius r2. As the gear rolls, it moves counterclockwise around the track at a distance of r2 minus r1, while the holes rotate clockwise around the center of the gear. For every rotation around the track that the gear makes, it rotates on itself some number of times. This ratio is given by the circumference of the path traced by the center of the gear over the circumference of the gear itself. We can model this motion using two sets of vectors. We have all of the pieces to our puzzle, now we just need to assemble it, starting with our two sets of vectors, one for the gear and one for the holes. Now we can break our information into three groups, each representing different types of transformations. Matching the geometry requires that we vertically dilate the equation. The default direction of rotation is counterclockwise, so to reverse the direction of rotation for the holes, we need to reflect the y component. And lastly, to affect the hole's rate of rotation, we need to apply a horizontal dilation.